2. Sibilant, sibilant, sibilant. Very good. Okay. Let's do this. Dark screen so you get better contrast. All right. Good stuff. Are other classes starting to hit you hard with midterms yet also? Yeah. Just kind of. Yeah. Oh boy, really? So thankfully we don't. Ours is not till week 10. So that's a pretty good deal. So just relax, do projects, just do the normal machinations of spinning through, doing your stuff, and then big assessment there at week 10. So we'll see that then. And we're actually starting to write it now, and the questions starting to look good. So we're trying to play with that on the TA side. All right, let's get started.
Wait, question on the midterm?
Question, yeah.
Will the midterm be focused on everything?
Everything up to the we'll share what it's up to. It will show it's up to. Everything up to that line. Yeah.
Okay, so
all right.
C and this bag.
Yes, indeed, and this stuff. Yeah, and this stuff. And SDS. Oh no, no. And SDS and data path and control. It's gonna be fun. All right. Have seats, folks. There should be room. Put your hand up if this is next to you. Come on, no saving seats. So come on in, ladies. Come on here. There's 1. Here's 2 there. There's 3 back there. Come on in, have a seat if you can. There's some seats in the back, I think. There's a seat in the back. Please do. Yeah, don't waste it. There's one here too. One more here. There's one more. Come on in. You want to come on? There's one right here. Come around. Here we go. Hold it there. She's gonna come around. It's easier to come around. Perfect. Awesome. Good stuff. And there's a chair, Mickey, if you want to borrow a chair too. All right, here we go. Let's get started. Ladies and gentlemen, welcome to Combinational Logic Blocks. Woo! All right. News of the day. I don't know if there's a mic. I don't think there's an extra mic, but it's okay. You can be loud. Minecraft. Who's a Minecraft fan? I love me some Minecraft. I play myself. I have my little world. I'm a chicken farmer, so I actually have a chicken area, and I go get my wheat and I feed. It's great. I love it. My 11-year-old turned me onto it. Using I haven't really played with redstone, but using redstone, you can make logic blocks. Look at this. These are the little logic gates, and you can make all the logic gates you want. Once you make a NAND or a NOR, you can make anything, and you can do this. So people, I'm to understand, people have built full computers in Minecraft. Full computers based on just like redstone. It's incredible. And wow, and program them. I didn't see that part.
I've seen somebody program.
Here, get the mic. Here.
I've seen somebody program like an editor,
Look at this, like a text editor.
Text editor.
Like Word. They're writing Word in Minecraft.
Not Word, but like something simpler. Text editor.
Wow.
Like Vim.
Like Vim. Like Word Perfect. Like Word Perfect. That's impressive. That's great. All right, good stuff. All right, here we go. What we saw last time, a couple things. If you have combinational logic, you want to pipeline in for a faster clock, which means, remember there was a delay on an adder, delay on a shifter, and we put a pipeline register in the middle so I can turn my clock faster, right? Why was that? What's my normal, who remembers what the equation is real fast of how fast you can turn up the clock speed? Faster frequency, lower period. Go, what was it?
T setup plus clock to Q plus
T, let's do time first. T clock to Q. Clock to Q plus combinational logic delay plus T setup. So this combinational logic delay is too big. You can slice it up and put a pipeline register right in the middle of that. That's what we saw. That I was trying to say. So they want to slice that big guy in the middle into smaller pieces. Perfect. You saw finite state machines, which is a finite state machine for trying to get 3 1s in a row. That was a nice thing. And you now have seen these pictures, but look at this. There's a missing arrow here. You can go from 3-way. By the way, I drew the same picture for CS10. It's true for you guys as well. I drew decimal, binary, and hex. You should be able to go from any one to any other one. Okay? What's missing here is you can't go from truth tables to gate diagrams. So if I have a truth table, what you normally have to do, as we recommend, is you then sum of products, each of the ones, you make a sum of those products. And then grab your massage oil to massage it to a simpler expression, and then you make the gates. Do you remember that? So you don't typically go straight from the truth table to the gates. You typically go through the Boolean expression to do that. That's why you see that missing arrow. We didn't talk about that really, but that's why you see that missing arrow there, okay? Sounds good. Today, data multiplexers, ALU, and one of the coolest adder subtractors you are going to see putting it all together. It's a really nice crescendo to this lecture. It's really very nice. We're going to have some fun today. All right. This is called a data multiplexer. A data multiplexer is somebody who, like a signal person at in some sense, you've ever seen if a bridge goes out or they're putting a construction on a bridge and you have to have a kind of one way or the other way on a bridge, you have to sort of yield, stop, and you have to have a signal person controlling that. This is one line, n bits wide, but I have two guys that want to drive that. And it's like, well, does A drive it or does B drive it? So this is a multiplexer, otherwise known as a mux. I only need one bit of signal to determine which one does it. If S is 0, A will do. By the way, we typically label these so that I know what value will drive it. If I don't have a 0, 1 here, I don't know who will get it. If it's 0, if S is 0, who should do it? So I almost always label the edges, the middle of the multiplexer to tell who does it. So when S is 0, A drives into C and B is ignored. Whatever B's value is ignored. If S is 1, then B drives C and A's value is ignored. Any questions about this mux? So this is an n-bit mux. Beautiful. We're going to use this all the time in our data path. This is next lecture. After this, we start to build our computer. We're going to need this because multiple things are going to be able to drive the same, say, input of the one end of the adder that we're going to have. We're going to have multiple. It could be. You could add. You guys know the difference between add and add-I. Add says register to register drives the adder. So the input to the adder, the plus, is 2 registers. Add-I is register plus immediate. So now all of a sudden I have both the immediate and the register as the second input to the plus. So that's why we'll use one of these guys to say what's that second input to the plus. Is it the register or the immediate? That makes sense? We'll see this next lecture. Okay? So here is a 1-bit wide mux. The same as the n-bit wide, but I just took the lines off. So whenever you don't see a line here, it's 1 bit. These are lowercase, you also think 1 bit. This is a 1-bit mux. Let's look at the truth table. How many rows in this truth table? We often ask how hard it would be to just look at the raw truth table to make this work. I'm hearing softly 8, not a loud, confident 8, but a soft 8, and it is 8, so that's right. Okay, well done. Why is that? Well, what are the inputs? That's a bit, that's a bit, that's a bit. That's 3 bits, 3 bits is 8 rows. Okay, so that's not too bad. And there's my truth table. We can verify this works. How does it work? Well, what do we got here? By the way, I've seen another way to draw this truth table, which is interesting, which says, is actually quite cool. It's 2 rows of truth table. I should almost draw it. Have you seen this before? This is really cool. Watch this. I'll do this in pen. I'll change this over so you can play with this right here. And those sorry, what's that?
Yellow.
Yeah, yellow and white. That's not so good. All right, here we go. Make it red. Let's make it red.
Yellow.
Okay, watch this. Here you go. By the way, I'm waiting for the new Apple OS update because I have my iPad Pro to be the second drawing thing, but the new OS will allow any supplemental iPad Pro to actually be like a tablet for any computer. It'd be kind of cool. All right, watch. I've seen this. Watch. S. I draw a line. C. Okay. Watch this. This is kind of cool. This is blow your mind. Okay. S is 0. What's C? A. Look at that. It's like I don't even draw the value of A, and I do this. So there's another way to do this where you do that. See that? Isn't that quite clever? That's quite clever, I think. So let's see if this is right. S is 0. What am I? Oh, I'm A. Look. 0011. 0011. It's exactly A. Like I collapse it to this. How about when S is 1? Is it B? Look, 0101. 0101. That's pretty cool. Okay? So that's not too bad. Can we... Right, question. Yeah, tell me front row. Tell me your name. Tell me your name again.
Rohan.
Rohan, go. Sorry.
But even with that correlation, then why not all of these have 1s in them? Because if S is C is equal to B, I don't understand. So
When S is 0, look at this. Watch it. When S is 0, C is exactly the A column. 0011. 0011. When S is 1, it's exactly the B column. 0101. 0101. So it's exactly like this. Kind of cool. So now, can we do some work to figure out what the actual combinational logic would be to make this work? We've got a truth table. We know how to do this. Let's see if we can do this together. And I drew all over it. All right, let's try it. Sum of products, right? Every time you see a 1 here, you say C equals, well, here's a 1. So this means not S, A, not B. Whenever you see a 0, you put a not in front of it. If you see a 1, you just write the term. So not S, A, not B, etc. for 4 terms. Let's use a little bit. What is this? What's the first? Who remembers their equivalencies that I showed that picture? What are the identities for that? How do we pull S out? That's the distributive property. It's reverse distributing the S out, okay? How do you pull the A out?
Identity.
This one. This is also distributive property, okay? B plus not B. Who remembers what that one was? I think the law of complementarity is what that is. That's my memory of this, okay? A times 1 to get A. Identity, right? So I get not SA or S times B. Look what I just wrote here. See this thing in red? Let's go back. Bloop, see this? I can almost go from this to make an expression. Isn't that beautiful? Watch this. Not S, A, or S, B. Look what I got at the end. Not SA or SB. Isn't it interesting? So I could do the whole machinery, or I could just really step back and say, look, when S is deasserted, when S is 0, then essentially I'm driving A. It's essentially A. Because look, one of these is going to be true, not S or S. So when S is 1, then this goes to 0 and it's just B. Because B times 1 is B. Isn't that beautiful? So that's really nice, just thinking about that. Okay? So how do we build this? Well, there it is. You've seen that before. That's not new. This is a review. Not S and A or S and B. Pretty easy. Okay? Not too bad. Yoink. Here we go. 4-to-1 mux. Here we go. A, B, C, D. Now, notice why we label it, right? And what's nice about this labeling is I'm going to say S, the vector S, has a higher order bit and a lower order bit. S1, S0. When that exact pattern of this bit and this bit are 0, 0, it's A. 0, 1, it's B. 1, 0 is C. 1, 1 is D. See if you can use the meta conclusion from the last slide to tell me straight, without having to go to the truth table, which has how many rows, by the way, here?
2 to the 6.
2 to the 6, which is 64 rows. You want to draw a 64-row thing and start working on it? I don't want to. So let's be smart about it. How do we go, based on the kind of meta-analysis, the cognitive meta-analysis you were doing on the last slide, can you give me the new version of that expression right now? Let's do it. Let's do it together. Go. Go ahead.
Not S1.
Not S1, not S0,
A.
A, or go. Not S1, S0, B. Get it? Isn't that kind of cool how we're doing it together? Or go. S1, not S0, C, or S1, S0, S0, D. With the thing? As row is there, and there it is. Isn't that beautiful? That's really cool. That's like the aha things I want to make sure you guys walk out of this. And this is not just one of those classes where you just grind away, right? This is about stepping back and really having some, this is what we call chunking when you're thinking about dividing things into bigger chunks. You want to just think about things in larger chunks. You certainly don't want to do that really arduous manual process of doing the 32, 64 rows of this. That'd be crazy. Be a lot of algebra to get to that. That's kind of cool. All right. Is there any way to do this? If I want to build this box, could I build this out of circuits you may have seen before? I don't know, maybe 2 slides ago? How do I build this without having to actually go to this? I could do this. I could go here and build these, and build the gates to do this. Or I could go to Fry's and say, you know what, Fry's, you sell other things I've shown on this slide before. How could I build that box out of things that are smaller, maybe? Yeah, go ahead, man.
Get 3 multiplexers.
3 multiplexers. How would you wire them up?
In a triangle.
Yeah, like an NCAA tournament. Like a triangle. Beautiful. Well done, my friend. Well done. So check this out. This is really cool. S0 is going to control who wins this first round of the tournament. And it's shared. This node means this is a connection, which means it drives here. And this means it's going under that. So it's not connected here. So it goes through here, and it connects here. So S0 is determining who wins of the A, B versus CD. It's almost like the Final Four. And if you ever watched basketball at March Madness, any Final Four in World Cup.
The one that you.
That's the kicking thing. That's the kick. That's what the hockey puck. Yeah. So Final Four, and then S1 is who wins in the final game. Isn't that really neat? Now, what's funny about it is, if let's say A wins. Let's say S0 is 0. Let's say they're both 0, 0. Who should win? 0, 0? Well, A comes through, C comes through. Oh, I'm excited, I made it through the first pass. I'm into the next round. And C goes, because it's 0 for S1. So it's kind of funny that all those things are live, but it gets blocked here just the same way as it gets, any input gets blocked in this mux if it's not being chosen. Isn't that kind of fun? Yes, question.
Can we save on gates if we go directly from the algebraic expression?
Good question. Good question. The answer is it actually the case that I would save on gates by doing this? If I did the arduous mechanical process, could I save on gates? Turns out that the system, computers are pretty smart, and so the systems, it's better if the point of view of an architect to specify this using this, and then it'll turn out that whatever the equation for this is, it'll work it out to be the right thing. So it turns out that just let it go. It's much better not worry about the fact that you're going to save an and and an or. There's a million transistors, billions of transistors now. The difference of this is very minor. And it actually makes more sense to logically think of this way, so build it that way. So that's nice. A good point, though.
I mean, you can run it through a compiler. It's like it's another compilation stage. So
Right.
You can have all sorts of optimization on this.
Yeah, I'll repeat it. I'll repeat it. Yeah, there are lots of optimizations you can have for the thing that takes this block diagram, the block system, and then compiles it down to the actual gates you need to do that. So it'll think about that and do that. Just like, look, you could hand author RISC-V for the rest of your life, or you just trust the compiler that's mostly going to get you there. That's kind of what we do, right? It's mostly going to be fine. Okay. So now let's talk about the next level. This is all pretty much this is not a lecture that's going to make your brain hurt at all. So this is kind of fun stuff. The ALU, we call it the arithmetic and logic unit. This is your main unit, your main block that's going to actually do some work for you. And so far, we have only talked about how to do a mux. We haven't talked how to build this yet. So let's actually try to build this today. So in general, this black box is going to have two 32-bit inputs. This S is going to be the kind of controller telling me what do I do. So it's almost like a higher order function. You remember a higher order function, you pass in functions of data? This is what tells you what function to write. This is like the input of the function. Now it's coded 00011011, but it's kind of cool that here's the function I'm doing it, here's the data I'm doing it on, and here's the table. If it's all zeros, it should add them. If it's 1, it should subtract them. If it's 10, it should AND them. If it's 11 or 3, it should OR them. And there's the result. That's pretty cool. Now, this is a simplification because I'm not showing you what happens if there's overflow and just be easy for now. Forget the overflow, just do the add and ignore if there's an overflow. Only keep it in the 32 bits wide. Okay, if there's any overflow, just wrap it. Just wrap it. Okay? So let's do it. Here it is. Look at this. This is such a cool slide. A and B come in. They are simultaneously, this is hardware. All of these things are working at once. It's not like, well, sometimes there's this one. No, they're all live. It's adding it. It's doing the hard work of adding it and subtracting it. Maybe only doing one of those based on this signal line. It's doing the AND. Even when I ask for an add, it's doing the AND. It's hardware. We can't stop it from doing the AND. It's doing the OR. If I ask for an add, one of these will be selected, and then what will happen? S1 is going to be 0. If I'm asking for an add or subtract, even though it's doing its work, it's being ignored down here. So all those 3 boxes are turning on all the time, and they're switching and they're doing the thing that they do, and there's delays, all those things. And at the end, I choose between whether I'm doing a logical guide, which is 1. Remember this, you look at this bit, right? If this higher bit is 1, it's doing a logical operation. If its higher bit is 0, it's doing an arithmetic operation. Arithmetic and logic unit does both. So there it is. You now know about a 2-to-1 mux. That's easy. We just learned that now. We haven't built this yet. This is trivial to build. How do you build this? It's a bitwise AND. It's literally 32 ANDs. You know what AND is? Just put 32 in parallel. Bitwise OR. That's easy. This is the part that's more complicated. Okay? Any question about this before we dive into what the adder subtractor is going to be? That's the goal of today's lecture, is to explain that. All right. So, how do we do the adder subtractor? 2 different ways. Truth table. Let's do a truth table. I'm pretty good at my Boolean algebra. Let's go. How many inputs to this guy? There's 32. There's 32. 64. There's 1. 65. All right, let's go. Get your pencils out. 65 inputs. How many rows? 2 to the 65, which is 32 XB. That, my friend, is too many. We're not doing that. We can also break this down into smaller pieces. Come on, let's do it. We got time. Yeah, all right. Or you could break this down and cascade things or hierarchically do them out of smaller blocks. Like go to Fry's, build 32 or some more number of other smaller things and wire them together in a clever way, like we did for the mux, right? Let's try that. Let's do the second way. So let's actually look at just the elements of this. Let's actually look at a single bit. We're trying to build an adder subtractor. The goal of this is to build an adder subtractor. Here we go. The lowest order bit. The lowest order bit. Just that's it. We start with the lowest order bit. This is a nibble adder, right? 4 bits adds to 4 bits, outputs 4 bits. Let's look at a single bit, the lowest guy. I only see 4 rows. Only 2. It's a 1-bit input, 1-bit input. This is an output. This is the sum, and this is the carry. 0 plus 0 is 0 with 0 carry. 0 plus 1 is 1 with 0 carry. 1 plus 0 is 1 with 0 carry. 1 plus 1, ooh. It's 10, right? 1 plus 1 is 10. Which is 0, 1 carries, right? You got that? So that's it. Anybody see what block implements S0? Take a look at it. XOR. Isn't that kind of interesting? What block implements C1? And. Isn't that cool? Right? It's kind of fun, right? Blink, XOR, and AND. It was in your answers, but that's pretty cool. Questions about that? It gets harder. Yes, question, Infermo.
Yeah, so you basically look at the two, do you basically just look at the 2 blocks, the two inputs for both blocks and just check what the...
I just look in here, write down all the possible cases, and that's all the possible cases. Very simple.
Oh, okay.
That's all I did. But now, I got some carry involved. So the lowest order bit is easy because there's no carry into that. Now we got to go to the harder one, the next bit over. Now I got 8 rows. Okay, this is a little bit harder. This is A and B. Now this is actually the ith row, general rows. I got an A and a B, and I have the carry in to that, coming in from my neighbor. Let's look at it, okay? Do you agree that if the sum of all the ones here is like the flipped version of this? It's like a 2-bit value with this is the higher bit and this is the lower bit. Why? 0 plus 0 plus 0 is 0. There's 1 0. It's just 1, right? It's like flipping this. It's like the number 1. 1 with no carry. There's 1 1. 1 with no carry. There's 1 1 with no carry. Oh, 2 1s, 0 with 1 carry, which is 10, right? 1 plus 1 is 10, so that's really 10, okay? Because this should be in that. We should fix this. Let's make a note. This should be in that column, just so it kind of reads like a number. All right, 2 1s, 10. 2 1s, 10. Uh-oh, 3 1s, 3, right? What's 3 in binary? 1 1. So it's 1 with 1 carry. You got it? Okay, so that's the truth table. What are the blocks that implement this? Let's take a look. This is harder, and you may have seen this before. I'll put my finger here. Go ahead. What have you seen before? What block implements SI, and what block implements CI plus 1? The carry out of that guy. I hear an XOR in there. Who's XOR? SI is XOR, isn't it? Remember, XOR is 1 when there's an odd number of 1s. 3, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, everything else is zeros. Perfect. That's XOR. I love it. SI was XOR, okay? CI plus 1.
Is it
And is rare. And is only a 1 at the bottom. So that's the thing from there. The majority circuit. You remember the majority circuit from a million years ago?
Oh, brilliant.
Never knew you would never use it. But now you'd use it. Let's take a look. Is it always the case? Let's look. 3 1s. That's the 1. 2 1s and a 0. That's a 1. 2 1s and a 0. That's a 1. 2 1s and a 0. That's a 1. 1 1. 2 zeros. The majority of that is a 0. Boom. 2 zeros. Majority of that there. 2 0 0. All 3 0 zeros. Majority. Ladies and gentlemen, majority. And if you remember majority, it is AI, AC, BI, BC. Pretty easy. We did this before. That was all from last lecture. That's pretty cool. I'm pretty happy with that. There's your SI. There, folks, is your CI plus 1. That's not bad. And we show them last lecture. It's kind of like tying it back to last lecture. You never knew I was teaching majority until now you know, right? It's kind of fun when I was, it's like a good joke. You set it up and then next day you deliver, yeah. Okay, so we take n 1-bit adders and I string them together. Yoink. That's pretty cool. Remember, we're trying to avoid going to 2 to the 65 rows and work out the logic. We can just build it out. I go to Fry's. I'm making a 32-bit adder. All right, Bob, show them where the 1-bit adder is. Yep. And you go in and you pick a big, okay, I got 1, 2, you put 32 in a box and some wiring and you walk out and you got your 32-bit adder. That's quick. Make it.
Anybody knows, raise your hand if you know what Fry's is.
Okay. If you don't know what, thank you for that. If you don't know what Fry's is an electronics store that's available in the West, it's only West Coast, California.
It's like Amazon,
Indiana.
like what it used to be where you bought stuff.
It was wonderful. It basically was Radio Shack done right. Like it was, I mean, because Radio Shack went out of business, but it was like you could buy, drives and wires and low-level stuff and high-level stuff, TVs and washers and little teeny transistors. Amazing. I mean, it's really wonderful. Radio Shack never got as big as kind of that space. And they've done well. I think they're still running, but every big business store is not doing as well as online stores. All right, here we go. Any question about this? I've got myself my adder. I don't yet have a subtractor. That's a little annoying. So I have to build the whole thing again for the subtractor. Let's think about how we do that in a second. Let's also talk about overflow. That is always an issue. And this slide, every single year, we got to do something with this slide, never is enough to get people over the thing. Is overflow just C sub n? Like last carry out. Like the box I bought from Radio Shack, by the way, had a carry in, a carry out, 2 inputs and 1 output. It had that. That was the box. I bought 32 of those guys. So A, I don't know what to put here. I don't know what I should put here. What should I do with this one? Ground it, right? I put a 0 here. Ground this guy, because I don't want to be adding 1 every time. That makes no sense. So put a 0 here. And what is this? Oh, there's my free output line. Well, is it the case that actually is overflow? Is that a nice way to signal overflow? I'm seeing some nods. I'm feeling good about that. Is that feeling good for people here? I like it. Except, give me an except. Well, I mean, except for the fact that if I'm using an int, like the first thing you learn whenever you use int, you don't type unsigned. When you first learn how to program and drive, you type int, right? So what's int of -1? Int of a equals -1. What's a? Tell me the bit representation of a. All ones. Okay, all ones. Can I add -1 to -1? Say sure. Is that overflow? No, because I can store -2, right? All ones. And all ones. I happen to be encoding a negative number because I'm using a signed representation. All ones and all ones. Do I get a carry out here? Yes, I do. All ones and all ones. I better get a carry out. Come on, all 9s plus all 9s. Don't you think it carries over? Yes. So, but is that overflow? No. It's not if it's signed. Is it overflow if it's unsigned? Ah, yes. So, with unsigned, it is overflow. With signed, it's not. And we have to think about how to do overflow with signed. That's the harder part. So, this is the slide for 20 years. It tries to explain how to do overflow with signed versus unsigned. I'm going to go really slowly, and I actually was on track to be able to spend twice as much time on this slide. Here we go.
Until I ruined it with Fry's.
Yeah, Fry's ate into this slide time. Here we go. I'm going to consider a 2-bit signed number. I want to try to figure out, do it really right, small. Okay, by the way, Polya's How to Solve It. There's a book called How to Solve It by George Polya. It says, whenever you have a problem, make it small. Understand the small version, then work your way back up. So let's try to do a 2-bit number, okay? A 2-bit signed number. Who remembers what the values you have for 2 bits? It's 0001, 1011. But what are you encoding with those numbers? Remember in 2's bit, is 1 extra negative number. You remember that? With like signed numbers, it's 1 extra negative number always. So, -2, -1, 0, and 1. Okay, that's what we got. So if we got to first get to that's the level. Let's level set. You got to be able to understand that first. So, if it's 1, 0, what number are we representing? Let's think about it. That's negative. How do you know?
Well, because first bit is signed.
First bit of sign is negative.
The rest are zeros, so it's the most negative.
It's the most negative, right? The rest of zeros are most negative. Exactly right. The rest of zeros are most negative always in all cases. Okay. You also know that 1, 1, always all ones is always negative 1. In everything, always all ones is negative 1. And that's one smaller than that. So that's, okay? That's minus 2. Now, if I'm going to add minus 2 plus, what are the cases I get overflow? Minus 2 is the smallest negative number I have. I can't get any smaller than that. So any overflow would be any other negative number. Does that make sense? Minus 2 plus a positive number is not overflow. But if minus 2, I'm literally my back, who's my camera? My back is to the wall. I can go no more smaller numbers in that representation. If you add any negative number to me, I can't go into the wall. That's overflow. Does that make sense? You add a positive number, I'm fine, because there actually is more negative numbers than positive numbers. So even if you added the biggest positive number, it's not an overflow. Because in this case, the biggest positive number is a 1. Minus 2 plus 1 is minus 1. I can still do it. Okay? So, the only time I get an overflow in this case is minus 2 or minus 1 if I add it to minus 2. Okay? Next one. If I have 1, 1, what's 1, 1? Negative 1. You should say that. Let's like lock that one in. That's tattoo worthy right there. Boom. Okay, right there. Minus 1, all ones is negative 1.
That's where the
Henna, the henna.
the other side.
The other side. That's the other side. That's the other side. So, if I've got a minus 1, now I'm no longer against the wall. Here's my wall. I'm no longer against the wall with my minus 2. I'm 1 bigger. Now I'm minus 1. What other numbers in the space of minus 2, 1, 0, and 1 can add to me and get overflow? Only minus 2, right? Because if I had another minus 1, I can still do that. I can still encode that. So only minus 2 is going to mess with me there. You got that? Yeah. So if I have 1, 1, only minus 2 is going to call me the overflow. Are we okay? I'm trying to go slow so that everybody's on the same page on every single bullet. Next one, 0. I add 0 to anything. Can I get overflow? Nope. Impossible. Because if you could encode it, then 0 doesn't change it, and you could still encode it. You got that? That's easy. How about 1? Now I'm at the maximum number. What other possible number in the range of minus 2, minus 1, 0, and 1 can cause overflow if I'm 1? 1, right? Because I'm the biggest. Well, only at 1. You got that? That's the only case you have overflow. So now, this may be the first time ever we actually get people over the hump on understanding this. Let's look at the highest adder. Those two numbers were coming in as B and A. I think there's an error. That should be B0. This somehow never got fixed. That's a B0. That's crazy. That's B0. Okay? Sorry about that. Look at this highest adder. Fix that if you can. Post on your slide. Sorry about that. Okay, highest adder. Here we go. Now, I'm going to only look at the carry in and the carry out of this adder to determine whether I'm going to have overflow. Okay? By the way, you all know, sanity check, if it's all unsigned, it's only carry out, right? It's only the top guy. Unsigned, I just look at that carry out for unsigned. This is the hard deal of thinking about signed numbers. All right. And by the way, I'm making the argument that we can do this in 2's complement, in 2 bits. Turns out this actually works for n bits. If I just look at the last two guys. All I'm really looking at is the highest adder. I'm waving my hands that it works, but it does work for n bits. Looking at the highest adder. Okay, here we go. Ready for this? Watch this. Here we go. I'm taking these bits and adding them to each other. So watch this. This is minus 2, this is minus 1, 0, and 1. Okay, let's walk together. I need like Al Gore, I need like a forklift to get me up here. Okay, here we go. No carry out or carry in. What does that mean? That means this was a 0 and that's a 0. When is that? Look at all the cases. When is there no carry in? When is there no carry in? Interesting. Ready this? No carry in or no carry out. It feels like it's 0 added to...
I hate to break you.
Yeah, go.
Can you do it
With a pen? Do it on the thing?
Yeah, because otherwise 11, like 1,000 students.
Well, but they can see my screen though. Yeah, I think I did it last week, and I hope that they can see my screen. But no, I like what you're saying. But But we can record it. No, well, no, you, no, you, no, I'm just saying, you, okay. When is there no carry out? I'll sit down. I lose like half my energy when I sit, but I'll try to keep the enthusiasm. All right, here we go. When, no, I'm gonna try. When is there no carry in? When did these two not get a carry in? The only time these got a carry in, look, this is, we ignore this because this is the lowest, this is a 2-bit number. This is 0. You guys read this is a 0? We're just doing a 2-bit number. Okay. When is there no carry in? When is this guy a 0? When it's like 0, 0, or 0, 1, or 1, 0. That means there's no carry in. You only get a carry when it's like 1, 1. You got that? Okay, let's look at these cases. Now, when does this have no carry out? Okay, so there's nothing coming in here. For no carry out means, what are these patterns? 0, 0, 0, 1, 1, 0. Okay? What are the combinations in here that is this case? Well, let's look at this. It can't be these two numbers together because those ones will add together to do that. That won't be so good. Okay? So it has to be this plus anything. I think that plus anything, right? So this is like 0 plus anything. I don't care. That's a 0 plus star. Okay? So I got that covered. What else is the case where it's no carry in or, actually no carry in or no carry out? So when else is it?
1 plus -2.
1, look at this. How about 1 plus -2? Do you agree that these two guys have no carry in and no carry out? And that's okay, right? Look, no overflow, right? You agree that 1 plus -2 is okay. Because, right, it only does have overflow when 1 adds to 1. So this is, I'll put a comma here. So this is 1 plus, I need a better tablet, 1 plus -2. That's only so far, so good, right? Anything else have nothing coming in and nothing coming out. What else? Give me something else.
1 plus 1. 1 plus -1.
1 plus -1, that's going to be a carry in. That's 1 plus 1 is going to carry in. So that's not okay.
Okay.
So I think we're okay. I think it's this one, all right, so far? I think that's it. Next one. Carry in and carry out. Let's look at that. When is it carry in and carry out? Well, carry in better mean that was a 1 here. If there was a 1 here, that means I had to have a 1 and a 1 there. If it's a 1 and a 1 there, that means it's either -1 plus -1, or -1 plus 1, or 1 plus 1. Those are the things. But it says carry in and carry out. If I add 1 to 1, is there carry out? No, 1 plus 1 is 2. That's not a carry out. Like in the unsigned number, 0, 1 plus 0, 1 is 1, 0. There's no carry out on that. It didn't overflow 2 bits to store 1, 0, 0, 1 plus 0, 1. How about these two? Can I do this? How about 1 plus -1? Is that okay? Let's try that. Do I get carry in and carry out? I think I do, because 1 plus 1 is 2, 0, 1 comes in. That 1 plus this 1 is 2, 0 plus 1 carry out. So this case is 1 plus -1. And is that an overflow? No, right? We just talked about it. Now, how about -1 plus -1? Do I get that there also? I do also. What's 3 plus 3? 6, right? If I just do this unsigned, 6. So that's going to be no overflow. Why? Watch what happens. 1, 1 plus 1, 1. Can you guys do it? 1, 1 plus 1, 1 plus 1, 1. Here we go. 1 plus 1, 0. I get a carry in. This is the carry in, okay? 1 plus 1 plus 1 is 1 and carry out. So that's there. But watch what happens. Is that actually overflow? Is -1 plus -1 an overflow? No, look. So that's also, look. So this is -1 plus 1, plus -1, plus -1, okay? And guess what, folks? No overflow. You guys okay with that?
-2.
Okay. Next one. Carry in, but no carry out. That says A and B are both greater than 0. What does that mean? See, the only way to have no carry out but carry in is 1 plus 1 here. If you look at this, 1 plus 1, that gives carry in. And then there's no carry out because it's 0 plus the carry in is 1, no overflow. No carry out. If any of them are negative, if I have carry in, that only means minus 1 plus minus 1. But then I also had carry out for that case, which I wrote over here. See? So this is 1 plus 1 only. 1 plus 1 only. And guess what? 1 plus 1, does that have overflow? Yes, we wrote it down. 1 plus 1 only. Last case. Carry out but no carry in. What's that from? Minus 2 plus anything. Watch this. Minus 2 plus anything. 0 plus 1, that's no carry in because 0 and 1 doesn't have a carry in. 0 plus 0, no carry in. But the 1s in the negative is going to have a carry out. So that's minus 2. Plus, minus 2 plus either minus 1 or minus 2. Did I cover every case? Look, there are 16 cases. These 4 numbers added to these 4 numbers. It's a grid of 4 by 4. Did I cover all 16 cases in these guys below? That's my question. 0, I got the 0 row. Minus 2 plus negative guys here. Minus 2 plus positive 1 here. Minus 2 plus 0 here. I got the minus 2 covered. 1 plus 1 here. 1 plus negative 1 here. 1 plus 0 here. 1 plus negative 2 here. I got the 1. How about negative 1? Negative 1 plus negative 1, negative 1 plus 0, negative 1 plus 1, negative 1 plus 2. I got all 16 cases are here. So in summary, the only time that I have overflow is carry in but no carry out, or carry out but no carry in. I went really slowly and pedantically through this case just to be able to appreciate this thing. This silence tells me that I lost some people, and every year we lose some people. But the point of this is, if you step back, if you don't care about the details of this, all I care about is this. That's when overflow and sign happens. Carry in but no carry out but no carry in. The working up to that is what I was trying to do, but it's a lot of being able to do math in your head with 2 bits, and it's harder to do that. Question, yes. Tell me your name again. Yoshila, go.
So basically, you only get an overflow when you have like XOR carry in, carry out.
Exactly. Yoshila's going to the next. You know what's called a plant. You know what's called a plant? Because I'm going to ask you, what operation is carry in but no carry out, or carry out but no carry in only those 2 cases? And Yoshila said XOR. Ladies and gentlemen, XOR. Thank you. Well done, by the way. Well done. Isn't that kind of cool? So, in summary, signed, I look at the XOR of these 2 inputs to the top, to the high level adder. Unsigned, how do I do overflow? Carry out, just carry out. Remember, overflow means you can't store it. But signed, I have to actually XOR these 2 guys to get it. You got that? Okay, I got time. Here we go. This is going to be perfect. This is, ladies and gentlemen, arguably the coolest slide in 61C. Short of what I'm going to show you in exactly a week. Exactly a week when I show you control, I'm going to show you a slide that's going to blow your mind. This is the coolest slide up till now. And I'm sorry for all the slides that you had, Mickey, but this is just really good.
That's okay. I'm going to make more later.
Yeah, he'll outdo me later. We got this thing. Okay.
There'll be a time.
There'll be a time where we'll see some good stuff.
This is the good stuff.
I love it. I love it.
I'm going to tell Dan.
I'm so sorry. I'm so sorry, Dan, but this now it is. Okay.
There'll be a time.
By the way, you could have that. You could have a day where you always are better than, you say, oh, this is the smartest class in Berkeley's history. It could be. You could be the smartest. The next year I can say it again. It could still be true. It gets smarter every year, right? Could be the case. Here we go. I didn't talk about subtraction yet. We have an adder. Here's my adder, okay? Cascaded adder of 32-bit, 1-bit adders. I got that, right? That was easy. Went to Fry's, 32 1-bit adders, some wires. I got my adder. Here's my overflow for a sign. This is my signed overflow. I should have labeled this. This should say I'm right. This should say signed overflow, right? Because that's not the normal overflow. This is unsigned. This line is unsigned overflow. I won't write the whole thing. Unsigned overflow. Unsigned overflow. And this is signed overflow. You guys okay with that? So yeah, all right. XOR has this really cool pattern. It's called a conditional inverter. Why is that? If I were to look at X and Y in the, this is XOR, right? 0, 1, 1, 0. You've seen it before. Nothing special. But watch this cool. I'm going to even zoom in. It's so cool. I'm going to zoom in because it's literally so cool. Now watch this. XOR has this feature in which if one of the inputs of XOR is 0, it just copies the input over. Look, it becomes Y. You get that? If, however, one of the inputs is 1, it flips it. It's called a conditional inverter. I have a line that I want to sometimes invert and sometimes be normal. I plug into an XOR, and that line of whether I invert it or not is the other line to the XOR. This says invert or not. Invert or not. Not copies it over. Invert. Bloop. I did it. Thank you very much. Isn't that kind of cool? You can control an inverter with a knob. It's kind of cool. Invert, don't. Okay? You got that so far. All right. Who knows what the equivalent, I need another equivalent algebraic expression for A minus B. Someone give me something other than A minus B. Go ahead.
A plus negative B?
A plus negative B. You get that? This is the best part. I would like to make a subtractor out of this box. This is an adder, right? I gave you an adder, right? This is an adder, okay? I'd like to make a subtractor. So how could I say A plus negative B? How do you negate a number that's a signed number? You flip all the bits. Oh, you mean like pass all of B through a conditional inverter? Now finish your sentence. You flip all the bits.
And then you add 1 to the...
And I add 1. How did I add 1? I got this carry in to the low order bit that's 0, which means nothing was being added. I could add a 1 to it. So if I say this is going to be subtract, this is the coolest slide. Is it right?
Yes.
This is a conditional subtractor that when subline goes high, a 1 comes in, B gets flipped, and it becomes A plus negative B because the bits of B became negative B.
Hold on.
Go. Become assassin.
And you remember when we looked at the instruction set of how you convert it into bits? The difference between sub
And add
and add?
was 1 bit. Was 1 bit. That 1 bit goes right here.
Oh, brilliant.
Isn't that amazing? XOR is an inverter. Give me a second. Can I hold a second? Because I don't think I have time for the question. All right. I'll answer your question now. Yell key campaign. Here we go. Truth table for a mux with 4 bits of signal. Like the signal line has 4 bits wide. It's 2 to the 4 rows. We could cascade n 1-bit shifters to make n 1-bit shifter, to make 1 n-bit shifter for shift left logical and shift right logical. The shifters, the things that move left and right, could I cascade them in the same way like go to fries by n of these 1-bit shifters and do that to cascade them to make it n 1 n-bit shifter? Let me turn the mic off and I'll answer your question. Yeah. All right, here we go. Almost done. Here we go. Yell key campaign. I had it ready. I had it right here. And go. 28 responses out of 100. Come on, give me some love. 3, 2, 1. Give me 100 people here. 30. Okay. And out of the 30, you're mostly giving me an F and a T. I'm mostly getting an F and T out of 30 people. Here we go. Answer. You said F and a T. Can I make this happen? You say F. I say, what? They're supposed to like type something. I don't know. This is a little PowerPoint. Okay, 4 bits of signals controls 16 inputs. 4 bits of signals. It's like 4 bits of signals. The signals are not the data. That's the signal line, the S line. So that controls 16 guys. 4 bits is total 16 possible cases. That's 16 possible lines that are coming in. Total of 20 inputs. That's 2 to the 20 rows. Certainly not 2 to the 4 rows. And 2, could I cascade n-bit shifters? The answer is yes. Feel free to go to Fry's and buy some 1-bit shifters. They're just sliding left and right. So that's very easy. Just like a normal, like the carries slide over. A shift left logical could just shift things left and right by exactly 1 bit. Wonderful. In summary, F and T sounds good. Yoop, animation. In summary, here we go. Perfectly on time. 400. Use muxes to select among inputs. S inputs selects among 2 to the S total lines. S input lines to the S total lines. Each input line can be n bits wide, by the way, input independent of S. I could be selecting from among 4 things. Each one could be 1 bit wide or n bits wide. It's actually another dimension to that. Muxes can be implemented hierarchically. ALU can be implemented using a mux. We just saw that today, where it's a very simple ALU. And we can certainly cascade. So n-bit adders are actually done using n 1-bit adders with XOR on input. That's that coolest slide ever, which we just saw there. Thanks very much, folks. I'll see you on Wednesday. Woo! And we're done with this section.